Welcome, and thank you for joining today's webinar. This session is the second installment of our sample preparation series. The first explored important considerations in the analysis of fused beads. I'm with our host, Frederick de Wits, and joining us, our invited speaker, Paul de Pape. Together, they bring over 60 years of hands-on industrial and analytical chemistry experience across XRF and deep expertise in sample preparation. As Paul says, his experience is your experience. Please use the chat to ask questions at any time, and any questions we don't get to will be answered after the webinar. Just a little bit about XRF Scientific. It is an ASX-listed Australian company, which was founded in 1972 and headquartered in Osborne Park, Perth, Western Australia. We manufacture and market precious metal products, specialized chemicals, and analytical instruments across Australia, Canada, and Europe, operating three core segments of capital equipment, precious metals, and consumables with a global manufacturing, sales, and distribution footprint. Today's presentation covers pressed pellet preparation. We will walk through key steps that make pellets reliable, particle size and homogeneity, binder selection, consistent pressing practice, pressure, and simple QC checks to catch preparation errors before analysis. Whether you're aiming to reduce repeats, remove bias, or improve throughput, this session will give practical, lab-ready guidance you can start using right away. And with that, over to you, Paul and Frederick.
Thank you. Thank you, Jackie, for this nice introduction. Hello, good afternoon from Brussels, where we are in the XRF Scientific Studio, where we will guide you through this webinar about pressed pellets preparation. So let's start with a short introduction about the all-over objective of elemental analysis. So the question is really, why do we want to do elemental analysis? This is, of course, to obtain precise and accurate analytical results to control product quality or eventually to steer our production processes. So keywords here are precise or precision and accuracy. We will see later on in the presentation why these are so important. So we must take care that the series of processes are being controlled, because these processes can lead to potential sources of error. And of course, these we all want to avoid at any time. And today we will study the pressed pellet sample preparation methods. So as I mentioned, accuracy and precision are two important parameters. Precision is really the repeatability or reproducibility of the measurement. And accuracy is really the proximity of our measured analysis, our result, to the true value. It's not always like this, that the measured value is the true value, as we will know. And here we can put the first question. So why is my analytical result wrong? And mostly, at least from my experience, the answer was, well, the X-ray spectrometer doesn't work properly. Or let's say the most logic answer is that one. It can, of course, be that our instrument reproducibility is not good enough, maybe that the quality of our standards is somehow doubtful, or that the calibration that we have set up is maybe somehow missing certain parameters or corrections, or maybe we simply didn't maintain our calibration over time, such that we have now today bad results. But we also have to think, of course, about how is our sample taking process, and especially how is our sample preparation process, because these two, sample taking together with sample preparation, can make up to 80 to 90% of our total analytical error. So it's not always the right answer, the spectrometer doesn't work properly. Mostly the answer is in the sample preparation. Now, before we decide how we are going to prepare a sample, there's a couple of parameters we need to take into account. This is the physical form of the sample size, but also the amount of sample, the sample quantity that we have. How much time are we prepared to invest, or are you allowed to invest to prepare one sample? Do you have like 1 minute, or do you have 1 hour to prepare a sample? And this generally goes hand in hand with the preparation cost of the sample. So there is a difference between, for example, preparing a loose powder sample or preparing a fused bead sample. The cost is differently, the preparation time is quite differently. And of course, also, again, this accuracy and precision will play a role. And when we talk about precision, we also talk about detection limits. So we have seen in our former webinar, we have spoken about fused beads, and there we have seen that results quality is really good, but that the cost and time and efforts are somehow higher than when we are going to prepare a pressed pellet. So their costs and time is somehow reduced, and the results quality is still very good, but maybe, at least for major elements, it can be less good than as for fused beads. But we will see for pressed pellets, we will have better results for certain trace elements. So detection limits will be better. Now, if you look at the sample preparation process, first of all, we have to do the sampling. And the sampling can be, for example, we have here a shipload, and we need to collect a representative sample for that bulk material. And this bulk sample is in general many tons of material. So we need to try to obtain a laboratory sample that is representative for this bulk material. So from those many tons, we go to a sample that contains maybe 100 to 1,000 grams, which goes into the laboratory where we use equipment that XRF Scientific has available to reduce the sample to the right size, but also to have a representative sample. Then this sample needs to be prepared into a specimen, and we will use, for the pressed pellets method, we will use a press, we will use many other parameters, as we will see, to obtain the specimen, and the specimen is the sample that goes into our spectrometer. So it is, of course, important that we follow very nicely the procedures, the processes of obtaining a very representable sample for this initial bulk sample. Now, some important parameters for pressed pellets. Well, first of all, the keynotes for pressed pellets are the following. Pelletizing, is the process of making pressed pellets for XRF analysis, where the main objective is to obtain a homogeneous and compact solid sample. So homogeneous, compact is very important. Why pressed pellets? Because it is the sample in its purest form. I mean, there is no dilution or almost no dilution. We have it as it is in its natural form, and this is very important. It is also quite cost effective and fast to prepare a pressed pellet, and the sample preparation is really very easy. And we have improved detection limits when we look, for example, at geological samples where we want to analyze trace elements. A sample in its purest form is always the best, and we can obtain really very good high quality results. Now, it is very important that we press the sample, that we compact the powder under consistent conditions. This means we always want to use the same conditions, same dilution, same everything. And it is a finely pulverized powder that we make into a dense and void-free disc using a die and the press to obtain a specimen that can easily be analyzed with our X-ray spectrometer. So read also here, void, air-free. So this means by making this compact disc, we are losing the air that in general we have in between the grains of our sample. So a first step is the pulverization, where we're going to reduce the sample grain size into very fine particle to minimize the grain size effects, and at the same time to increase the homogeneity. Then we're going to add to this fine pulver a binder or maybe a grinding aid to increase the cohesion of the particles and to improve also the grinding process. Then we are going to fill in this mixture into our press die, and the press die is going to give the shape to our sample. So depending on the amount of sample, the kind of sample, we may use a smaller or a bigger die size to create our specimen. And eventually we can also use tools like aluminum cups or anti-sticking films to help us preparing better quality discs. And at the end, we're going to press. So we place the die into a press that can be manual, semi-automatic, or fully automatic. Frederic will talk more about all the types of presses that XRF Scientific has available. And generally, we're going to use or to apply a high pressure, which is generally a couple of tons. Now, some key considerations to assure high quality. So first of all, we need to reduce the grain size effects. And in next pages, we will continue talking about all the details here, grain size effects to avoid contamination, to take care that we have a nice homogeneous sample, to select an adequate binder, and thus also dilution, and to use appropriate pressing conditions for the sample size and weight that we want to create. So the first parameter is particle size effects. And here I'm just showing a simple example where we have just like silicon oxide and aluminum oxide grains. And in the first case, the upper graph that we can see here, we can see quite large grain size, and our X-rays will penetrate into our sample, and X-rays will come out of our sample. And the analyzed layer really shows the depth from which we get information from our sample. And this analyzed layer depends really on the element that we are analyzing. Like sodium is a light element, so the analyzed layer may be very small, maybe just a few micrometers. And for heavier elements, like for example iron, this analyzed layer may be deeper. Anyway, when I'm going to reduce my grain size, it may happen that the relation between the aluminum oxide and the silicon oxide particles changes. So it may be that we have a different amount of particles in our analyzed layer or our analyzed volume, really. So we have to be aware that the measured intensity for each element in our specimen that we want to analyze is a function of the number of particles into our analyzed volume. So decreasing the particle size may thus have a strong influence, but it's something we need to do. Now, when we reduce, or how can we reduce now the particle size effect? So I've done here three tests. So the first one is I have done milling of one and the same sample. If I remember well, it was a clinker sample. I did first of all not grind it, so 0 seconds, and I ground it up to 300 seconds. And we can really see for all the elements, and we can see here silicon, iron, magnesium, and calcium. But so for all the elements, we can just see a very light intensity increase. Yeah. And as soon as I'm going to grind the sample with a swinging disc mill, we can see this here, we can see going the intensity up. So a swinging disc mill is really swinging very rapidly. It grinds really much finer than such a mortar mill. And when we take the sample that has been ground by the swinging disc mill and we're going to press this, we can see a high increase in intensity, especially for, or mainly for the light elements, but also still for the heavier elements like iron. You can see for magnesium here, we can increase from more or less 40% relative intensity to 100%. So we get very high increase. So this press pellet really takes care that we have huge intensity increases. Contamination from the grinding vessel can also happen. We can see here an example of a quartz sand that was ground, and the original sample is the red scan. So we can see no contaminations. But when I'm using a zirconia vessel to grind the same sample, I can see here appearing contamination, of course, of zirconium, but also of yttrium. Yeah, unexpectedly. So if you want to analyze, for example, a geological sample in which you want to analyze zirconium and yttrium, you should not use the zirconium oxide vessel. So there's different vessels available on the market, and depending on what your analytical needs are, you can select the vessel. So if we take, for example, the tungsten carbide, which is generally used, we have to be aware that tungsten, cobalt, but also carbon will contaminate our sample. So we must be aware, if I want to analyze cobalt or tungsten in geological sample, maybe it's not the best choice. Yeah. So we are not always aware that we contaminate, but contamination can also come really from the sample that we ground before. Yeah, if we grind let's say an iron ore, and the next sample would be a quartz sand in which I want to analyze traces of iron, I would have a completely wrong story for the iron result if I haven't cleaned my vessel before. So what we can see if we are now going to dilute, or yeah, it's dilution, yes. If we're going to add binder to our sample, it does have a serious effect on the intensity of our elements that we want to analyze. For example, for iron, so the upper one, and it's maybe difficult to see, we had a 9-gram sample and 0.5 gram wax. And for the lower one, so the green peak, we had a dilution of 9 grams of sample to 2 grams of wax. So we can see a very clear difference in intensity here. And this is even more obvious for magnesium, so for a light element. And here we can really see huge differences in intensity. So we understand that it is important to have very strict condition and always use the same amount of binder for similar types of samples. And another one I could not leave out, because people analyzing geological samples may know that the Compton peak is very often used for correction, maybe an internal correction or just simply for a matrix correction. And also the Compton peak is, of course, being influenced by this binder effect. So, and here we can clearly see what is now the influence on the intensity. So again, 3 different elements, aluminium as the lightest element and iron as the heavier one. So we can see that for aluminium, depending on the amount of wax we use, 0, 5, 10, and 20% of wax we use here, we can see that we lose for aluminium like up to almost 40% of our intensity just by using this 20% of binder compared to not using a binder. That's very drastic. Also, the pressure has an influence, of course. So we have done the test here from 5 tons to 40 tons of pressure. And already by the color change, if you look here, you can see a clear sample and grows darker and darker, depending on the pressure. It is so that when we press with a higher pressure, that the particles become closer to each other. So they are more compacted, so there are less air voids. But in general, we stick to 10 to 20 tons of pressure. And this is a very good compromise in general. Yeah, so of course, when we use an automatic press, we may generate more precise repeatability. We can see the effect of the pressure. Well, yeah, again, here the 4 elements, calcium, silicon, iron, and aluminium. We can see again, iron is less problematic. We go from more or less 97% of relative intensity to 100%. So we lose only 3%, but this only 3% we can definitely not neglect, because 5% of error on a concentration of 10% is still 0.5%, which is a lot. Yeah. So we must take care that we always use the same pressure for same kind of samples. That's very important. So a simple test was done here to show you the critical situation that we are facing. So this was a biomass prepared in 4 different ways. So it's each time the same biomass, so each time the same concentration. And sample A here is the original sample, measured as a loose powder, and then the original sample was pressed as a tablet. Then this biomass was ground by a swinging disc mill, and then that sample was also being pressed. So what we can see here for iron, for example, if we look to the original loose powder, we have here an intensity of, let's say, 40 kcps. And when we look to the ground pressed sample, we see here about 60 kcps. So it's a difference of 20 kcps or 50% for the same sample that contains the same amount of iron. Yeah. So we can all see the difference here. Without pressing, there is still some difference between the ground sample and the original one. But as soon as we press the sample, as we have seen before, the intensity increases drastically. Silicon is even more drastical. So here we can see from 10 kcps to 30 kcps, or 3 times more intensity between the original and the ground pressed powder. So we can also have just maybe smaller amounts of sample, excuse me. And if you just have a small amount, maybe 1 gram or less than 1 gram, there's different ways to prepare those samples. We can always take as a base, and that's the white part here, a boric acid tablet. And then we can put our sample on the surface of the sample. So this can be a preformed boric acid, or this can just be a plain boric acid tablet on which we scatter some grains, or this can be a plain boric acid disc on which we can still add like a couple of millimeters of sample. So depending on the quantity of sample that we have. Now, there is a difference between the pressed pellet and the fused beads methods, for those who have seen now both webinars, and especially when it comes to detection limits. First of all, we need to know what the lower limit of detection is. And this is defined by this formula, in general, defined by this formula. There can be some more parameters in there, but anyway. So we really depend on the peak to background ratio and the measurement time to define our limit of detection. So the better the peak to background ratio is, the lower the detection limit will be. That's the message, without going into more detail. So the concentration is defined by the measured intensities. So the concentration is really calculated by an external computer. The X-ray spectrometer only measures intensities. Now, when the peak to background ratio for pressed pellets is much higher than for fused beads, which we will also see on the next slide. So therefore, the detection limits are also considerably better. Now, calibrations for pressed pellets, on the other hand, are a bit less good than for fused beads, and that's because of grain size and mineralogical effects. So when we look here at scans and differences between pressed pellet and fused bead, so you can see the black scans are pressed pellets and the red ones are the fused beads. Like for sodium, as a pressed pellet, we have much more intensity than for a fused bead. And we can also see in the titanium to potassium range, we can also see that, see, the black peaks are always much higher than the red ones, so better detection limits. And also the mid heavy elements, gallium to nickel, again here, especially here, for example, for zinc, we can see a much better defined peak, a much lower background also, yeah, than for the fused bead method. So we can also already see the movement of the background is much flatter for pressed pellets than it is for fused beads. So these are all indications that detection limits are way better for pressed pellets. And that's at a certain stage, we can see, for example, here gallium. Here for the fused bead, we are not sure anymore. Is this still a gallium peak, or is this just movement of the background? But for the pressed pellet, we can clearly see, well, no, this is gallium. We can still analyze it by pressed pellet and not anymore with a fused bead. But as I mentioned, calibration curves, because of grain size effects and especially mineralogical effects, are not that good anymore, especially for, let's say, the lighter elements, the oxides, let's say sodium to calcium oxide, basically. Yeah. For fused beads, we have better calibration curves for those elements. So some other parameters and some advices to make pressed pellets. So dry the sample always before preparation, because liquid is simply not a part of your sample. We cannot analyze it, at least with XRF. It may be part of your sample when it is, for example, hygroscopic water or crystal water. Yeah, but we should dry the sample. Cross-contamination, avoid this, especially during the grinding and the pressing process. Eventually, pre-grind the new sample in your mill before you grind the sample that you will use for analysis. and always intensively clean the press die. You can also use aluminum cups to have more stable samples. They will keep the edges of the sample better together. And eventually you can use a sample film to put in between the powder and the die discs, so, such that it does not stick to the die. And generally this is a polyprop of 12 micrometer film that we are using. Always make sure that the specimen doesn't release particles in the spectrometer, of course, because it can contaminate your spectrometer, and costs may run high when you have a contamination. And always clean remaining particles eventually by using a tissue to not contaminate the X-ray spectrometer. So from here, Frédéric is going to take over and talk some more about equipment and the chemicals that are used.
Yes, thank you, Paul, for all this valuable information. And yes, now I will speak more about the equipment and the chemicals we have available at XRF Scientific that help to prepare good quality press pellet powder. So again, the manufacturing process include the grinding, so grinding the sample to find particular size. I will not go into details of all the equipment available for that because it's another long topic. Of course, mixing the sample with a binder or with a grinding head, or sometimes it's not needed if the material is soft enough. And of course, pressing the sample, the specimen between 2 and 40 tons. So generally we prepare press pellets powder of 20, 32 or 40 millimeter. And when we speak about sample hardness, of course, the condition will be different if we are dealing with ferroalloys, a granite or slags iron ore were considered as hard, or for the soft product like floor, wood, gypsum, who can be pressed without any additives, are really easy to form. So now speak about the binding and grinding agent. So first, what they do? So of course they improve the pelletizing. So we can see here a nice preset powder, fully homogeneous. So the binder, the grinding agent could be a solid or a liquid. The binder act as a glue, in fact, and being squeezed into the interstitial space between the grains and cementing together all the grains. So what we want is to have stable pellets. We want to have minimal dilution, like you explained it, about the intensities, the 4 light element, for example. No contamination by the binders or the grinding agent, of course. Easy to clean, so easy to release the tablets from the die. And no moisture, because of course we don't want to analyze water, but also we, if we work under vacuum, we don't want the pump is taking too much time to create the vacuum in the analytical chamber. Yeah. So now the most used binders, grinding agent are the wax, the liquor wax. This is probably the most used one. Cellulose, boric acid, polyvinyl alcohol called moyol, paraffin, polypropylene glycol, and some special mix including wax, cellulose, paraffin, depending. And generally the amount is between 5 and 30% by weight to obtain a good and strong tablets pellets. And of course, this is something you need to verify before to go to the spectrometer. So it's good to, for example, fold the tablets on the table from 10 centimeter and just to check that the press powder tablets is strong enough before to go to the spectrometer. And maybe you can remove a little bit the dust you have around the aluminum cups, for example. So, or you can add the binding and grinding agent to the sample. So we have first the vortex powder mixer. So in that case, you will mix the powder, the sample powder with the binder. And we will use a vortex mixer to have an homogeneous powder at the end. And this is what we use for the liquor wax, the wax, and the cellulose. So the wax, the liquor wax, is probably the most used binder. It works very well. You can really, I would say, solidify the powder with really a good strength, good condition, and the quantity that need to be added are not so high. 10%, 15% is totally enough to have a very good pellets. Cellulose is good too, but you need to add more cellulose in the powder. Cellulose can also be used as a grinding agent, so you can add in the grinder before. Now we can mixing and blending using a grinder. So in that case, the grinding agent are added directly before the grinding and mix it during the grinding process with the sample to obtain an homogeneous powder and obtain, of course, a perfect homogeneous pellets of the powder. And for that, we use most often the cellulose and the mixed tablets. So at XRF Scientific, we produce the XR tab, who are available in two composition. Or you can have tablets only made by cellulose with lubricant, but it's more than 90% made of cellulose. And in that case, the tablets weight 330 milligram, and then you will have the quantity, you count the quantity you need to have the correct ratio, so no need to wait, and of course it's an advantage. And we have the mix 55 with a mixture of wax and cellulose. So the advantage to mix the wax and the cellulose is to reduce the quantity of binder to add to the sample, and like you explained it, to maintain high intensity for all the elements. And we can surely with this type of mixture be below 10% by weight quantity of binder. With cellulose tablets, we need to add a little bit more, but we can do with the cellulose a more intense grinding. Depending on the case.
So less consumption and better grinding.
Yeah, exactly. So at the end, we have good self-binding properties using that, adequate grinding, abrasiveness, and of course the purity is good for XRF purpose. And high stability and moisture resistant, like I explained, we don't want to have water moisture in the pressed powder, and we need to leave the tablets close to the grinder or to the press, so we don't want these tablets are catching water. So it's very important. So now the case of liquid. So we have some plastifier, fusible plastifier that can be mixed with a solvent to produce a solution. You will add to the sample powder to after be able to produce solid tablets after drying. So the big advantage, it takes a little bit of time, but the big advantage is really like you make a solid plastified pressed powder. So it's very strong, and it's used for the fluffy powder, very pulverized powder, like black carbon, coal, that are really dusty. And if we can take two examples, we have the PMMA, so polyethylene metacrylate comethyl metacrylate, and this is a very good compound. So it's first dissolved using a mix of solvent, could be acetone, ethanol, hexane, and the big advantage, the solution take about 30 minutes to be prepared. But after, when you add that, let's say 2 milliliter to the sample powder and well mixed, it evaporates in 5 minutes. So you can directly press after the dried powder and prepare the pressed pellets. And of course, we have also the moil, who is also very well known. You can dissolve that in water or even in acetone, but it's a little bit longer. Then the sample support. So they are there to provide a strong baking. This is mainly recommended for all applications, but of course more for calibration standard if you want to keep them a longer time and reuse after. So it of course reinforce strength the handling, and for that the most used are the aluminum cups. So it's available in 32 or 40 millimeter, and you can have it in different form and shape, conical, so or straight. We call taperet for the conical and straight. We have also the plastic sleeve, so it's a little bit more, I would say, not common, but it works also very well. The steel rings also available in different dimensions, 32, 35, 40 millimeter. And the, like you explained already, the coat of boric acid, or the backing of boric acid, or free bore. Free bore because in some lab we don't want to have the boric acid anymore because it's classified CMR. So the steel rings, just to show you the different type of steel rings you have available. So it's mainly depends of the type of automated pressing machine you are using and adapted to the spectrometer. So they can be reused. So you can remove the powders after and reuse the steel rings. And then the sample, like you already explained, the layer of boric acid or free bore. And so we have some tools to prepare that. And again, it's made for the binders like boric acid or free bore. So the pressing equipment. So just speaking about the pressure, which pressure to use, most of the time is determined experimentally. So normally between 2 and 40 tons. And what we try to find is when we can see on the graph, so the intensity versus pressure for aluminum and silica. What we want is to have the good pressure will give the higher intensity for most of element of interest, of course. And we need to press up to obtain this plateau, and no need to press at the maximum if we can reach the good intensity peak for the element we are interested for sure. So the usual quantity of powder, I will say peak mix of binder and samples are between 6 and 8 for the 32 millimeter pellets, and between 10 and 15 grams for the 40 millimeters pellets. And the pelletizing time is not so important, to be honest, but nevertheless it's better to keep it about at the same time for each pellet. But if you put 10 or 20 seconds, it doesn't matter so much for the press tablet powder. So the equipment we have available, so we have the classical manual hydraulic press and also the electric hydraulic press. So these both press, so the XR press, are able to reach 25 tons. And so, to be honest, they cover nearly all the application you can find for all the materials. To be honest, we supply a lot of the electrical version because it's quite economic and easy to fit on the bench. We have a protective door, and the press are fitted with rubber suction feet, so they don't move on the bench. So that's very useful. Then we have also the pellet kits, and that's something really important because you want to avoid too much manipulation of the die. Maybe I will let you show that, but in fact we have a simplified handling. So it's a forceless recovery of the pellets. You just need to slide out the bottom part of the die, and no need to dismantle completely to recover the press tablets. So manipulation is very important in this case. So it needs to be relatively easy. And then we have pellet kits for the plastic sleeve of 20 millimeter. So it's also really easy to use. You even have a funnels to feed the die, and then you just lock the die, and the tablets is also easily ejected, so no need to do many manipulation. And this one is used for the portable XRF system because of the easiness of preparation. And we have also programmable hydraulic press, so Apex 400. So this machine is fully automatic. This machine is able to reach 40 tons, and it's a bench top press machine. So for 40 tons is quite rare. And the advantage is the easy loading with no handling of the pellet die kit.
That's right.
So
it's automatically ejected. Huh?
Yeah, exactly. And we have a drawer to load in, load out the powder. So just to explain quickly, here this is the case of the pressing in the steel rings, but you can also press in aluminum cups or even without any support. Right. So you load after the powder, you just put the cap, close the drawer, select the program, push start, and then when you hear the beep after 1 minute 30 seconds, then you can reopen the drawer and collect the sample after removing the cap. So it's really easy. You don't need to manipulate the die. So when you have high throughput, it's the best tool. Yeah. Like you explained, if we have risk of contamination, could be interesting to add a pellet film, so polypropylene 12 micron on the disc, the polished disc, or on the piston directly. So it avoids cross-contamination, like you explained, or if you have powders who can corrode the disc, or if you can have potential contamination by the disc itself. So if it's made in stainless steel, you can have some contamination of the metals. Yeah. So some application now. For clinker, cement, or geological product, if we want to produce beads of 40 millimeter, beads pellets of 40 millimeter, we will use about 12 grams of sample. We will grind with the tablets of XRTAP, Mix 55 or XRTAP C20. We'll use aluminum cups after so when we obtain the homogeneous powder, we use aluminum cups, and then we press just at 20-25 tons, and we obtain a very nice pressed powder. Here we gave the case of powder baby milk. Again, really easy here in this case. You just feed with an aluminum cups the dye with the milk, and then just press at 4 tons, and you obtain a perfect tablet pellet ready for analysis. Here the case of wood. Again, here we need to add a grinding head before the grinding to be able to have fine wood enough to press it. And we use isopropanol. We grind during 3 minutes. Again, we had an aluminum cup, and then we press at 5 tons, and we obtain a very nice pellet of wood sample. Here, another application, ferroalloy, ferrosilicium. So in this case, we have received granules that we crush in a mini grinder, mini crushers. Then after grind, to obtain a fine powder below 75 micron. Then we take 10 grams of this fine powder. We mixed with wax, liquor wax, 2 grams. and we press at 20 tones in an aluminum cup, and we obtain a very stable and homogeneous press.
And so XRF Scientific has all these tools available?
Yeah, exactly. We have all these tools, and they are the big advantage. They are very compact, so you don't.
It's quite interesting. It's all desk tools.
Exactly. Yeah, exactly. So that's what we have to prepare the tablets. So I let you finish, Paul.
Thank you. So I think we have seen that we need to be very consequent in preparing pressed pellets. It's very important, always using the same pressure, same amount of binder and so on. Because there's really quite some parameters that can influence the results. So we have to be aware, we have to reduce all the potential errors. And please remember that XRF Scientific has all the tools available that you have seen. And not only this, there is also the knowledge that there is available between us. And that's, of course, something that you can always use free of charge. So we have the knowledge, just ask us. We have the tools, just let us know, and we provide them for you. So, Jackie, I think I'm just going to leave here with showing our contacts, and I'm not sure if you still want to spend a couple of minutes on questions and answers.
Thank you, Frederick and Paul, for sharing your expertise. Yes, I see that there's been a couple of questions that have come through from our attendees. The ones that we don't get through to today, we will follow up after the webinar, so please rest assured. But maybe we can tackle one if we've got some time. There was a question that came through around the ideal thickness of a pellet. What we need to consider, considering the various atomic weights of the various elements, especially if one wants to quantify the light and heavy elements. Can the same thickness be applied to the pellets in order to do the wide range of analysis, and what are the limits in millimeter?
I think I'll get that one. Is that okay for you, Frederick?
Yeah, please. Yeah.
So we know that X-rays that come out of the X-ray tube will penetrate our specimen. And depending on the elements or elements that will be analyzed, we will have different energies that will come out of that specimen. So in general, and don't be surprised what you hear now, a thickness of, let's say, 5 to 7 millimeters for almost all samples will be just fine. But please be aware that for light energies like fluorine, K-alpha, sodium, K-alpha, the thickness of analysis may be just a couple of micrometers. And for the heavier elements, depending on the matrix, of course, this can be up to a couple of millimeters, but not more. So if you have a light matrix like wood, and you want to analyze heavy elements like iron, maybe also calcium, or lighter elements like magnesium, sodium, we are good with a pellet of, let's say, 5 to 7 millimeters. So an ideal thickness, I say, use this 10 to 12 grams of material and you're fine for all elements.
Great. Thank you so much, Paul. And then maybe if we've got time for a last question, one of our attendees has asked how to use the Compton intensity as a correction. Do they need to correct all the elements by Compton scattering?
No, this is not possible. You know, I can talk 2 hours about this topic, which I won't do. But let's say the Compton peak can be used for all the elements that come beyond the Compton peak until the first high absorption peak, and then it finishes. So which in general is iron K-alpha. But depending on the matrix, this could also be zinc or tin or whatever matrix you're looking at. So Compton peak is very much used for geological samples, and for geological samples, iron is mostly the main absorption peak. So everything lighter than iron, forget it.
Yeah, fantastic. Well, I think that's it then for us tonight. I would like to thank everyone for attending, and thank you again, Frederick and Paul. And we hope the practical tips on the pressed pellet preparation, particle size, homogeneity, the binder choice, the pressing technique, and the quick quality checks that one can do gives all of our attendees the immediate improvements in pellet quality and their XRF results. And for all the questions that weren't answered, we will answer that in the next coming days. And then our webinar will also be available on our YouTube channel. So we will also, of course, supply the links to our webinar. And yeah, we look forward to seeing everyone at our next webinar. Thank you so much, everyone.
Thank you.
Bye-bye. Thank you
Bye.
very much.
Bye-bye.